Dear listeners, dear fellow researchers, my name is Marko Lange, and I will talk about an alternative approach to Ozaki's scheme for error-free transformation of matrix multiplication. And this is a joint work with Professor Rump, who was working on an alternative evaluation scheme for dot products in higher position. And then we found some parallels to Ozaki's original scheme and thought about various improvements, and about these I will talk in this next 25 minutes. So I packed the slides quite full. I will not be able to speak about every detail there, but I still wanted to show most of it, to leave it open for later discussion. So don't be surprised if I skip over some parts of the slides. So let's directly start with a short recap of Ozaki's scheme for evaluating the matrix product A times B in higher position. And the idea is pretty much straightforward. We split the matrices A and B into k plus 1 parts, just like this. So the sum of these parts, of course, should still represent the actual matrices. And A1 is the most significant part, and A underline k is the least significant part. And this is done in such a way that all these parts have a limited range of mantissa bits. And this is chosen in such a way that the individual dot products of these parts, the parts of A and B, so AI times Bj, can be evaluated using floating point arithmetic without introducing rounding error. So then Ozaki's idea is to reformulate the matrix product like this with the right-hand side here. So this follows straightforward from this identity for A and B. And be collecting the significant half of all the k plus 1 squared terms in the first sum and combining all the other terms in k plus 1 remaining terms. So when evaluating the right-hand side of 2 with an accurate summation algorithm, then the floating point error, so overall error, is determined by the individual floating point approximation errors within the matrix products of the k plus 1 remainder terms. And since they are the least significant terms, so the overall position increases. So to be more specific about the condition that ensures evaluation without rounding error, let's consider a dot product of two vectors A and B. So if we assume that A is element-wise integer multiple of some mu, and B is an element-wise integer multiple of some nu, which are both powers of 2. And the entries of A are bounded by 2 to the power of alpha times mu, and respectively for B, it's bounded by 2 to the power of alpha times nu. Then we know that all the entries of A have the same restricted mantissa range of alpha bits. And all the entries of B also have the same restricted mantissa range of alpha bits. So we can interpret it more or less like a dot product of integers if we just shift these matrices corresponding to mu and nu. So then this condition more or less follows straightforward. If n times 2 to the power of alpha times 2 to the power of alpha is bounded by the inverse of the relative rounding error unit, then the floating point evaluation of A times B, the dot product, is evaluated without rounding error. So in the original algorithm of Ozaki et al., this condition is just ensured for all individual dot products within the matrix products AI, Bj. Yeah? And this allows us to reduce the error, which would typically be n times u times the absolute wise matrix product of the vectors, by a factor 2 to the power of minus k times alpha. Because for every split, we have we cut alpha bits out of the number, the most significant. So with every split, we gain a position of alpha bits. Yeah. So first, we will generalize this for arbitrary basis beta, show a slightly different splitting approach and some other possible improvements. And at the end of the talk, I will give you an alternative evaluation scheme. So for this, we suppose that our floating point system has a base beta and a mantissa length p. So our error constant u is defined as 1/2 times beta to the power of 1 minus p. We assume the absence of overflow and actually also the absence of underflow errors, but this is explicitly stated in the corresponding results. And for the final summation, we make use of the fast to sum algorithm. And this is here just given exemplary to show that we work on matrix entries, which has the benefit that we reduce the interpretation overhead in languages like MATLAB and so on. And also I want to use it here to introduce the notation FL for mapping into floating point entry, and float to state that all the individual operations within this expression are done in floating point arithmetic. Yeah? So let's go to the first modification to the original algorithm, and this is a different splitting algorithm. Actually, if you look at the splitting algorithm, you might say this is pretty much the same. It more or less looks identical. Indeed, the only difference is that instead of the sigma in the original paper, which is a certain power of 2, we use here this magical number to split at a specifically given splitting point mu. And this is actually not really a magical number. We could think about many numbers that satisfy this. But what is important is if you apply the split algorithm, which is more or less just the same as in the original paper, and this condition should be satisfied, then A will be split at a splitting number mu, which is the power of beta, yielding 2 output numbers. Yeah, and this pair satisfies the condition in form. So the sum of these 2 numbers will just represent the original floating point number A. So A prime, the first part, is the integer multiple of our splitting number, and the remainder part is bounded by half of this splitting point. And this condition is the big difference to Ozaki's original approach, because there, if you use the power of 2, then depending on the sign of A, that might be true or not. Yeah, so there we lose 1 bit in the precision. Or other way, by applying this splitting scheme with specifically given mu and nu, we gain a factor of 2 in precision for every split that we do. So in the actual application, we want to split into k plus 1 tuples. So here's just the generalization. This is very much straightforward and can be computed just using top to bottom approach, just applying split to first split to the most significant part, and then recursively split the remainder parts until we have the k plus 1 tuples that we are looking for. The second major difference to the original approach is the condition that we use for ensuring that we use to compute the splitting points, for which we can ensure that the floating point evaluation then will be error-free. So in the original paper, we had this n times 2 to the power of alpha times 2 to the power of alpha should be bounded by the inverse of u, which is now with arbitrary base beta, like this beta to the power of p term. And this 2 to the power of alpha is just the natural upper bound for the maximum entry of the vector divided by the corresponding splitting point. Yeah, but this can be seen as n times the infinity norm of A times the infinity norm of B divided by the respective splitting points, which should be bound by beta to the power of p. And here we replace this by the product of the 2 norms of the respective vectors. And therefore gain another factor in position, roughly factor 2, but it depends a lot on the problem at hand. Yeah, so because n times infinity norm times infinity norm is of course upper bound for this, and the smaller we get this guy here, the smaller we can choose the splitting points mu and nu. In the practical application, we have alternative condition using QA and QB, which should be bounded, that product should be bounded by beta to the power of p, and then we can choose minimal mu and nu, powers of beta, that satisfies this condition 7 here, and then the condition 6 is implied, and therefore for the splitting that this is satisfied here, we know that the significant part is calculated floating point arithmetic without rounding error. So we have here some additional guy for the condition number. So we can exploit the condition number of the problem if we know it. To weaken the condition and then choose even larger mu and mu. But for the sake of simplicity, I just show it here and will not really talk about it. So our problem at hand is a matrix product. So instead of choosing individual splitting positions for every dot product within the matrix product, we choose the same QA, the same QB for the rows of A and the columns of B respectively, so that the condition 7 here is satisfied for all rows and all columns of all rows of A and all columns of B, so that it's satisfied for all individual dot products of the matrix product, and therefore can split the complete matrix and then also evaluate all the individual dot products just as a matrix product. And by applying this approach recursively, we can, just as in this original approach, ensure that all the matrix products AI, Bj are evaluated without floating point error, and they can be evaluated using efficient level 3 BLAS routines. Yeah? A small but very important difference to the original approach is also that we don't recompute the splitting points for the main terms, but we pre-compute a constant factor between the splitting points that still ensures that all these products are evaluated without rounding error. And by using the same constant factor between all these splitting points, it's possible to group the intermediate results according to the significance within sets here ZL, yeah, which are just the set of all the products with the same sum of indices. And the big benefit of having the constant factor here is that all these products have the same properties. So they are all matrices in the set are bounded by beta to the power of p times tau to the power of L times mu times V transposed and mu transposed, and are element-wise integer multiples of this guy. Yeah. So all of them have the same p mantissa bits in the same range, not the same p mantissa bits, but have the same ranges of mantissa bits that can be non-zero. And this means that they can be represented more compactly just using two matrices. Yeah. So given this condition, then it can be proved that just the compensated summation algorithm, if you apply it to all the matrices within such a set, that the resulting matrices SL and EL, their sum is just identical to the sum of all the matrices within the set. Yeah, so the condition, there's a restriction on the number of matrices, and there's a slightly stronger condition on the upper bound of the matrices, which can be ensured by requiring that QA times QB should be bounded accordingly, and of course this tau also need to be bounded accordingly. But this restriction is really more or less just the same as before, so it's a very slight restriction in addition. And this allows us to represent the sum of all these individual matrix products, which is growing quadratically with k, in just two k floating point matrices. Indeed, the error terms satisfy the conditions for the set of the next order, so it can be reduced further with these matrices. And actually, it's sufficient to use k plus 1 matrices to represent the sum of all these matrix products here. And this is a very practical choice, yeah, to do so. For instance, if our problem dimension is extremely large, then we would like to break the original problem into smaller subproblems, because if n becomes too large, then the gain and position for each additional split becomes smaller and smaller. And if n would be extremely large, then this scheme would not even be applicable anymore. Of course, it would be a very tough problem either way, but just in general, so it might be beneficial to split to break the original problem into smaller subproblems. And if we choose the same splitting points for all these subproblems, then we still have just the k sets for all individual matrix products over all of these subproblems. So we still just need k plus 1 floating point matrices that serve as accumulators for all the individual matrix products. And the computational overhead is relatively small because for every matrix product, we just need 4 matrix summations into the accumulators. And over this, we might just skip over this. It just shows that, again, applying the compensated summation approach on the output, these k plus 1 accumulator matrices that already represent the large sum. If we evaluate again a compensated summation over these matrices, then we get a faithfully rounded approximation. Yeah. And additionally, if we keep the error terms, then just by adding 3 times k minus 1 additional matrix sums, we get a twofold position. And adding another 3 times k minus 2 additional matrix sums, we get threefold position. So it's outputting it in a multiple position via unevaluated matrix sums is just more or less for free. So the overhead for this is minimal. And this can be used for evaluation in higher precision in general. So as a very small example, and I will just skip over this and come to the more interesting part on the next slide. So if we have A times B times C, for instance, and want to evaluate it in the K for a twofold position, then we could apply Ozaki scheme to the first product, A times B, and produce an output, an unevaluated sum, U plus V, which is a twofold position of this product. But now it's not necessary to evaluate U times C and V times C separately and then merge the unevaluated sums. But we intend to solve the problem just by produce a splitting of this unrelated sum directly. So we produce a splitting M1 till M underline 4 just of the sum directly and use it directly as the input for Ozaki scheme. And this means applying this for higher position evaluation is just more or less for free. So we just can give it as a, take it as an additional gift of this algorithm. It's very nice, actually. But let's come to the last topic of this talk, an alternative evaluation scheme. So, as I said before, if we evaluate the matrix product A times B as a product of these sums of k plus 1 parts, then we would have k plus 1 squared matrix products. So Ozaki et al., they reduced it, almost half it, by combining the less significant half into k plus 1 remainder terms. Here we go a slightly different direction. Here we collect only the remainder terms that actually involve remainder parts, like this, and only have 2 remainder terms, and keep all other products in the significant sum that we actually want to evaluate. So for k greater than 2, this would be actually more complex than Ozaki scheme. However, it allows us to apply fast multiplication strategies for large integers to reduce overall complexity. And on the next 2 slides, I want to show how we could apply the Kazoo algorithm to our problem. So let's just assume k is equal to 2. Then we would split the matrices into 3 parts. And here we scale the middle parts with the constant factor between our splitting points. And this has the advantage of ensuring that they have the same splitting point, that they have the same splits and can be added without having to rescale the things. So then we use Kazoo, which is just the application of the quadratic equation, to reformulate the sum of these 2 products as the product of these 2 sums minus these 2 products. So we have to evaluate these either way, and instead of additionally evaluating these 2 products, we just need 1 additional product. So we can rewrite A times B as the right-hand side of 11. And instead of the 6 matrix products that we would have in Ozaki scheme, we now have 5 matrix multiplications, but in return for some additional matrix summations. And additionally, we have to ensure that this is evaluated without rounding errors. So we have to restrict the conditions we have to make the conditions on tau and QA and QB a little bit tighter. And then we also apply some similar transformation as discussed on the previous slide to make the sum here more compact. Yeah. Just for the sake of completeness, I want to show it for the case that k is a power of 2. Yeah, in this case, we just would take the lower half, call the function recursively, the upper half, call the function recursively, add these two halves, call the function again. And here we just see the same difference as subtraction as we have seen on the previous slide. So this would be T2, T1, and T3. Evaluated, merged, unscaled, renormalized. So not going into the details here, but in general, we would just get the output, and it's not so difficult to realize and implement. And that this actually gives a benefit in computation time can be seen on this small numerical example. So we consider the product of 2 square matrices with dimension n just 1500. And then we see from the timings that actually the approach of Kazoo is faster than the original approach. DD stands for double-double, so we use a double word arithmetic for the final summation to make it more or less fair comparison to the others. And the modified approach is still Ozaki scheme, but with our modifications. We see a gain also a gain in position, which is not extremely large, but at least we see that there is a gain. And particularly nice is actually the gain in computational speed due to the application of Kazoo approach. So in this talk, I discussed the modifications to the splitting of the original algorithm of Ozaki, and which results in slightly higher precision. I've introduced an efficient summation algorithm that is specifically designed for the output, the manipulated output of Ozaki scheme. And we have introduced an alternative evaluation scheme that reduces the complexity from k squared to k to the power of log 2, 3 matrix. But there have been also some points that we didn't have the chance to speak about. Yeah? Unbalanced generalized splitting setups and exploitation of sparsity was already discussed in another paper of Ozaki et al. Also the Tom-Cook generalization of Kazoo approach. There will be one last slide where I just want to show it, but not really time to discuss it here, or possible further reduction if you could split the matrices on the fly. So the references on Kazoo's approach, on the original paper of Ozaki, the generalization where they also speak about applying the application of sparsity and so on. And then just so that you have seen it once, how the application of Tom-Cook for k equals 3 would look like. We see that things become much more complicated and involve much more matrix summations. So the benefit is only for very large dimensions already, but I don't have an actual implementation. So this would be left for future research. So thank you for your attention, and I'm looking forward for fruitful discussions.